about now? Okay, today we're going to go over the next layer of things with graphing concepts. We have a couple more days of this, and we're going to start by doing some algebra review. I'm going to do a very obscure algebraic process that all of you did probably in an intermediate algebra class. You probably did well. You've completely forgotten it because you've had no reason to ever go back to this obscure thing. And it's like many things you learned in an algebra class, you learned it with absolutely no idea when you would ever use it again. And we're going to use that thing today. How many remember doing partial fractions decomposition in pre-calc? Very powerful thing. And of course, you spent 60 to 90 minutes of your life doing these problems without any idea where you would ever use these again the rest of your life. It becomes hugely important in Calc 2. In which case, I will reteach it from beginning to end because I know nobody remembers it because you only did it one part of one class with no explanation of where you would ever use it again. But the fact that you saw it makes it really easy on me when I reintroduce it because you've already seen it. So I'm just refreshing your memory. All right, today we're going to solve some inequalities, but not linear inequalities. So I'm going to start with something simple. I would like to solve, let's say, x squared is greater than 9. And we want to go all the way to the end so we understand the algebra and how to express an answer, because this is the sort of algebra we're going to be doing later on today. So when you solve this, do you just start trying to find numbers that make this true? I mean, certainly anything bigger than 3 would work. So is the answer x bigger than 3?
Or negative.
Or might there be negative? Oh, yes. The way you do this, I'll give you a hint off to the side. If I wanted to solve this, wouldn't the easiest way be to do this and then factor it? And then set your factors equal to 0? Well, it turns out, same thing here. We're going to start by doing it this way. I want the 0 on the right side. So now when I factor it, now I'm not interested yet in the direction of the inequality. I just want to make sure I have a 0 on that side. Now, every real number that I substitute in here is going to either give me a positive product or a negative product, except for 2 values. What values will neither be positive nor negative? 3 and negative 3, because it'll be 0 at those numbers. Do we all agree? This will equal 0 when x equals 3, when x equals negative 3. Every other real number will make my product positive or it'll make it negative. So I want to look at a number line, and the only numbers on my number line that are relevant are these 2. We have just partitioned the number line into 3 intervals. Everything to the left of negative 3, between, and everything to the right of 3. Now here's the nice thing. If I chose a number in any one interval and it made that product positive, then every number in that interval makes it positive. If I chose a number in an interval and made it negative, then every number makes it negative in that interval, because you can't go from positive to negative or negative to positive without passing through 0. And we just said these are the only places that ever equal 0. So the simplest way to attack this is to pick one number in each interval. I like being extreme whenever possible. Here's what I mean. Pick a number to the left of negative 3. I like using numbers like negative bazillion. Okay, can't really mess that one up. So if I put negative bazillion plus 3 is going to still be negative, isn't it? Negative bazillion minus 3 is still going to be negative. Now when I take the product of 2 negative numbers, what will I get? A positive. So I'm just going to shade above the line, give myself a mental image. Everything to the left of here gives you a positive product. Now, let's pick a number between negative 3 and 3. How about 0? Hard to mess up zeros. 0 plus 3, that's positive. 0 minus 3, that's negative, and the product of a positive and negative is? Negative. Now let's pick a number bigger than 3. Be extreme if you can. Positive bazillion. Positive, positive, positive. I have not looked at the direction of the inequality yet. Now I'm going to look at the direction. Which intervals will make this positive? Do we agree it'll be this one and this one? What if it had been a less than? Then I would have picked this one. The work I did was the same regardless of the direction of this. Does that make sense? Now, I could do an or equal, I could do a strict inequality. That's not important. It's how do I now read my answer? My answer is this interval, and I write them this way. negative infinity to negative 3, open at both ends, union 3 to infinity. So it's every real number in that interval. It's not the whole number line, because there's a gap of numbers, namely between negative 3 and 3, that would make it not true. So the way we answered this question is we've made our inequality, first of all, 0, and then we treated it almost like it was an equal to figure out these guys, right? Literally my partitions, okay? So far so good? You did this way back when. You probably were good at it. You've probably long since forgotten it because you have no reason to do it again. What if the problem was already in this sort of form? Let's say I said x plus 4 and then x minus 1 squared and then x minus 6. And I want that to be, let's say, I don't know, let's say less than 0. It's already factored. That makes my life a lot easier. Rarely do things come factored, but this is factored. Well, what are the only 3 numbers that I care about?
Negative 4, 1, 6.
Just make sure they're in the right order, by the way. Don't put 1 to the right of 6, in other words. All right, I partitioned my number line into 4 different intervals. So let's pick a number in each interval, like way that way. Negative, negative. It's going to be positive, isn't it? Because I'm squaring it. And that product would therefore be, I have an even number of negatives, so it would be positive. Now pick a number between negative 4 and 1. How about like 0? By the way, how many calculations did I do over here? None. If you're calculating, you're looking at the wrong thing. You're only looking at signs. And I said every number in an interval will give me the same sign. So it's not important what number I pick, but that I pick a number in the interval. So I'm going to pick 0 because it's hard to mess that up. 0 plus 4 is positive. I'm squaring this, it's positive. 0 minus 6 is negative, so that product is negative. Now pick a number between 1 and 6. You want to go with 4? Okay. 4 plus 4 is positive. That's positive. 4 minus 6. It's still negative, isn't it? Now pick a number bigger than 6, like way bigger than 6. Am I going to go positive, positive, positive?
Mm-hmm.
Yeah. Now, this one always makes me laugh. I'll do this problem for people in a calculus class and they'll say, oh, your intervals always alternate. Do they? They sometimes do. And that would be a correct conclusion. They sometimes alternate. I wouldn't even say they alternate most of the time. They just, no, if you just automatically make them alternate, you'll be wrong way too often. No, you got to do them one at a time. I wanted to know when this was less than 0. So I want these 2 intervals. Now this is kind of tricky how I'm going to answer this one. Is it negative 4 to 6? You're shaking your head. Why not? Because at 1, it equals 0. It's not less than 0. So how do I do that? I say negative 4 to 1, 1 to 6. And I am excluding 1 from my answer. 1 is not making this true. Because if I evaluate this at 1, I'll get equals 0. And 0 is not less than 0. Not a trick question, just a little tricky when I'm writing it. So would you say this is not really complicated? No. But this is what we're going to be doing today in every single problem. We're going to be looking at products and trying to figure out where our products are positive and negative and, of course, also equal to 0. Okay? And in doing so, we're going to be able to make some analysis of our derivative stuff. Okay, let's do a fairly simple problem. Let's see. Give me just one sec. Okay, so let's do f of x equals 2x cubed plus 3x squared minus 12x, try it here, plus 7. Now, what I want to do today is not just find the critical values. I want to keep going. I want to describe what the graph actually looks like. without necessarily even drawing it yet. I'm going to show you how to do this, and you can draw a fairly accurate picture. I'm going to show you how to draw a fairly accurate picture without actually plotting even a point. Because I need to know what the shape of the graph is. I kind of like to know where it is on the XY plane. I know one point. I know it passes through 0, 7. I could make a table of values, but that may or may not be helpful because the important stuff might not be happening in integer values. So the first thing we're going to do, like we did last day, is take the derivative. Let me get some of my pens here. Now, I said the first question you always ask whenever you're doing a problem is, what is the domain? Because if I'm doing all my derivative stuff and I get numbers that are outside the domain, I don't count them in my answer. What is the domain?
All real numbers.
All reals. By the way, all polynomials have domains of all real numbers. They're continuous everywhere. They're differentiable everywhere. Polynomials are wonderful. There's never going to be a restriction. Restrictions come when I have a logarithm, when I have a square root, when I have a quotient. Right? There will be restrictions automatically because there will be places that I can't have. This is not one. So this one's pretty friendly. So my domain, and I'm actually going to write it down. It's just good form to have that every time. Okay? Now, what's my first derivative?
8x minus
6x squared plus 6x minus 12.
Okay, I need to know where this equals 0, which means I need to factor it. Well, those numbers are too big, but if I factor out a 6, can that be factored? I'll do my part. Here, okay.
X plus 2, x minus 1.
X plus 2, x minus 1. Beautiful. Very, very nice. Now, in a calc class, more often than not, things actually work very nicely because we're trying to navigate to the end of the problem. I don't say this jokingly. In a calculus class, if you get an ugly answer, you think you did it wrong. You're in chemistry and physics. You get an integer answer, you know you did it wrong. It's not possible because you're doing measurements. No measurement can ever be an integer. There are an infinite number of possible values. An integer is not even one of the possible values. But in a calculus class, we want happy numbers for everything because we think we did it wrong otherwise. So I'm going to say, and this equals 0 where?
X equals minus 2.
When x equals -2 or when x equals
1.
+1. Okay, those are my critical values. I want to describe the shape of my graph though. I want to know, when is my graph going uphill? When is my graph going downhill? Where are the horizontal tangents? Well, I'm pretty sure the horizontal tangents are those guys. But I don't know, when is it going uphill, when's it going downhill? Because going uphill versus going downhill is a very different look. How the heck would I figure that out? I have an idea. Let's make a number line, and we'll call it the f prime number line. Now, how many places is the derivative equal to 0? 2. Why don't we put them both on here? And I'd like to know, when is my derivative positive? When is my derivative negative? Well, how the heck are we supposed to figure that out? Or is that what we've spent the last 20 minutes doing? Yeah, that's what we spent the last 20 minutes doing. I have a number line that is now partitioned into 3 intervals. Those below -2, those between, and those above +1. All I need to do is take one number in each interval to determine if it's positive or negative. So, if I go way that way, this will be negative, negative, and that product is positive. Take a number between -2 and 1. How about 0? Positive, negative. Now let's pick a number bigger than 1, like positive bazillion. Positive, positive. All right. I'm basically done with all the calculus for the rest of this problem, for the most part. Now I need to analyze what I just wrote. Now, this is the first derivative. The derivative tells me the slopes of the tangent lines, and when the slopes are positive, it means my graph is going uphill, it's increasing. I can now say absolutely, f is increasing and f is decreasing. Well, it's going to increase wherever the first derivative is positive. And the reason I keep saying first derivative is next day we're going to learn about the second derivative. And you're always going to do both in every problem. So the first derivative is positive here and here. So it's going to be increasing from -∞ to -2. and then again from positive 1 to infinity. My graph's going to be going downhill. It's going to be decreasing here. Okay, so I know my graph's going to climb for a while, then it's going to go down for a while, and then it's going to climb again. Okay? I would like to determine where my maximums and minimums are, if I have any at all. I can now tell without drawing a picture or even plotting a point. Now, we do want to find the y values. So let's calculate f of negative 2. Let's calculate f of 1. Extrema are the y values. Critical values are the x values. Extrema, highs and lows, maxes and mins. Those are the y values. So what is f of negative 2? Don't go to the derivative, go to the function. Let's all do that. Use your calculator if you will.
Like 27, unless I watched that.
This is giving me issues. There we go. I'm going to bring this up on Desmos in just a second. Okay. All right, so what's the value here?
27.
27, and what's the value here?
0.
I don't think so.
No, no.
How about, oh, is it? I'm sorry. I can't see. 2 plus 3 minus, yep, it is 0. You're right. Stay too far to one side. Okay. Can you tell me if either one of these is a maximum or a minimum? And actually, you can, and here's how you do it. It's very, very scientific. Okay? Erase this part. I don't need this anymore. I'm going to need a clear screen in a minute. Okay. This says I am increasing. And what happens when I get to negative 2? I have a horizontal tangent. And then what's happening in here?
Going down.
Going down. This says graph's going up, flat, going down. Think that's going to be a maximum or a minimum here?
Max.
It's going to be a maximum. Blank, because we're going to figure out local versus absolute in a moment. Now, I was going down, I was flattened out, and then I'm going up. What do you think that's going to be?
Min.
Don't look at the value. That's not how you do it. I'm going down, I'm flat, I'm going back up. So this is a blank minimum. What I just did is called the first derivative test. The first derivative test means you are using the behavior of the first derivative, whether the first derivative is positive or negative, telling me my function's increasing or decreasing, and flat. So if I'm increasing, I'm flat, and I'm decreasing, that has to be a max. If I'm decreasing, I'm flat, and I'm increasing, that has to be a minimum. That was pretty simple, wasn't it? By the way, do we even have a picture yet? No, we don't even need a picture yet. Now, how do I determine local versus absolute? This is the easiest part of any problem. This does not require any form of calculus whatsoever. It can't be an absolute max if there are other y values that are higher. It can't be an absolute min if there are other y values that are lower. As x grows without bound positively, where's this going? So can this be the absolute max? Nope. It's local because you just said it goes up forever. Now, as x grows negatively without bound, what's it doing? Therefore, when you have exponents like this, odd exponents usually means it goes in both directions, but even exponents means it goes in the same direction, either that way or that way. Think of a parabola that opens upwards. I have no maximum, but I definitely have an absolute minimum. If my parabola opens downwards, I definitely have an absolute maximum, don't I? So I can have an absolute extrema, but most of the time extreme are local. We haven't even drawn a picture yet, and we've just done a fairly accurate representation of this graph. Now, if I wanted to get more accuracy, I would plot a handful of points. And the points I would plot obviously would include these guys. So now I want to bring it up on the screen in just a moment. Let me change the scale. X-axis, I'm just going to go, I'll bring it in just a moment. Let's say we want to go maybe -5 to maybe +4. Oh, that would be perfect. Okay. Now, I don't know if this is going to catch or not, but it won't. It doesn't matter. It worked today. Maybe it needed the weekend off. Whoa. Uh-oh. Hold on. This is not good. Oh dear. Somebody's playing with the buttons. They're all selected at one time. Oh, here we go. Whew. Normally they're orange. They were all green. I don't think that's good. There we go. So what did we just say? We just said f of 1, which equals 0. 0 is the maximum, not the 1, the 0. Or, I'm sorry, the minimum. F of -2 equals 27. We're saying that's the maximum. Now look at your picture. There's my 0, 1. There's my -2, 27. Are they absolute? No, because on the right it's going to go up forever. On the left it's going to go down forever. So that's why they're local. I don't need the graph to tell me that. I just need to look at the function and say, oh, it's going up forever. That's not calculus. I'm just looking at the exponent. If I wanted to get an accurate graph, I would simply make a table of values. Now, the table of values I would choose, I would probably go from -4, maybe to +2, +3 at the most. Why? Because those y values are getting so big so fast that it's overkill to try to get that much in. Here's the mistake a lot of us make. We try to get a lot of x values in, okay? We try to go really big on the x, and so here's what we do. We'll say, all right, I'm going to make my graph, the typical graphing calculator is always -10 to 10, isn't it? So I'm going to go -10 to 10, and then I'm going to make my y's, So I'm trying to get everything in. Well, -10 to 10, I can't even see it, so I got to keep. Do you see a problem? I'm never going to get -10. I'm going to have to go really far down. But in doing that, it's going to shrink my graph. This part right in here, that's where everything's happening. I don't need to see the parts where it's going forever. Right? It's getting steeper and steeper and going forever. So you understand, I only need the parts where it's turning around and doing cool stuff. That's all I really need to get an accurate graph. So last day, what we did was we took the derivative, set it equal to 0, figured out the critical values, but we really didn't know where to go from there because we didn't have a way of testing them. We drew a picture, kind of worked backwards. So today what we're doing is we're finding the critical values, figuring out our intervals, and then making our conclusion based on that statement, not based on the picture. Doing something that allows me to see. Now, what if consecutive ones didn't change? That's an interesting concept. So give me a moment here. I'm going to reverse engineering something here. All right, let's do a new problem. I like to reverse engineer them so the numbers come out, relatively friendly. Okay, so let's do, how about 3x to the 4th minus 16x cubed plus 24x squared minus 6. That's going to be our function. Now, the degree of the polynomial tells you the most number of roots or zeros it has. In fact, going a step further, an nth degree polynomial has exactly n roots, but some of them can be repeated, some of them can be complex. Oh, you see, x to the fourth, what if it was entirely above the x-axis? Could I do that? In which case it has 0 roots, or it has a whole bunch of complex roots. This has as many as 4 roots. But that means it could cross the x-axis as many as 4 times. Then how many times can it turn around at the most? Well, what's the derivative going to be? X to the third, so therefore how many times can the derivative be 0?
3.
So how many times can this turn around? 3. Does it mean it will turn around 3? No, that's the most number of times it can turn around. So that's why we need to do derivatives. We can't guess what this looks like just from the degree, but the degree will help us because it gives us upper limits. Do you agree again the domain is all reals? Beautiful. So, what's our first derivative?
12x cubed minus 48x squared
Plus 48x. All right, can I factor that?
yeah.
It's a cubic, that's scary, but they're all x's, so I think I can factor an x out. What else?
12
So 12x, and what does that leave me?
minus 4
X squared minus
minus 4.
4x plus 4. Does that factor? Do you agree with that?
Yeah.
So how many roots do I have? I don't have 3, I only have 2. One of them's a repeated root. Aha. So this equals 0 at x equals 0 or 2. That's my f prime number line, not the f number line. So I have 3 intervals that I've just partitioned the x-axis into. And let's do exactly what we did a moment ago. Now, most people have had calculus at least once in here, if not 2 times or 3 times, and you have different ways of doing things. What I'm showing you is the simplest way to get to conclusion. It's also the fastest way and the most accurate way. I need to figure out where my derivative is positive and negative once I determine where it's 0. Right when we started derivatives, I said the most important thing is to know where your derivative equals 0. I have to have it in a factored form in order to do that. So we've got the equal 0 knocked off. Now you can also tell me where's the derivative positive, where's it negative, because that's going to be everywhere else. So if I go that way in a forever direction, what do I got? Negative, positive. Between 0 and 2, like positive 1. Bigger than 2 in a that way direction, way down that way. Huh. How many times do I turn around? Once. It's a 4th degree polynomial, but I'm only going to turn around once. Well, that's kind of interesting. So f is decreasing, or excuse me, increasing 0 to 2, and again from 2 to infinity. I do not say 2 to infinity because it's not increasing at 2. It's got a horizontal tangent at 2. So it's decreasing the rest of the time. You notice these have to be open intervals because where the derivative is 0, it's neither increasing nor decreasing. It's flat. It's not moving in this sense. What's happening here? I'm decreasing, decreasing, I flattened out, and then I went up. So f of 0, which equals what, by the way? -6, is a blank maximum or minimum? Minimum. If you're having to think about this, then you're looking somewhere else. You were decreasing, you were flat, you were increasing. That's it. I'm decreasing, I'm flat, I'm increasing. It's got to be a minimum. What about f of 2? I'm increasing, I'm flat, and then I am increasing again. Did I turn around? No. So f of 2 isn't anything. Ooh. Now, what it is, we're going to learn about in the next class. I'll give you a hint. It has to do with the second derivative. But right now, f of 2 is not important to us. We thought it was going to be important. It's got a horizontal tangent, but it doesn't change direction. So, absolute or local? X to the 4th power is going up in both directions, isn't it?
Yeah.
If x goes positively or negatively, it's going up. Therefore,
Absolute.
absolute. I'll put abs. That's it. That's how you measure conclusion. If I'm going up in both directions, then my min has to be the absolute min. It's the lowest it ever gets. Never goes below this point. It's kind of cool, huh? Now, let's see what this looks like. Oops. Sorry, try that again. What we've always done in the past is I've made a table of values and then we plotted a bunch of points, but it's correct, but it's kind of inefficient. Now, okay, check this out. What did we just say? F of 0 equals -6, absolute minimum. It's going up, flattens for a moment, and then keeps going up. That's kind of cool, isn't it? Something interesting is happening there, but it's not turning around. It does have a horizontal tangent. X equal 2 is a critical value. It gave me 0 for the derivative. But I did not turn around, and I know that because of this statement right here. This is how I know it didn't turn around. It went up, flattened, and continued to go up. And we did that without having to look at a picture. The picture now just confirms what we said. I'm decreasing, I got to 0, I flattened out as increasing, flat, increasing. You could have all told me that that was the shape of the graph without plotting a single point. You just wouldn't have known how stretched out it was, but you would have known it actually looked like that. This comes through practice, but it doesn't come through point plotting like you did back in algebra classes. That is kind of a waste of time. Because when you're plotting points, you're just mindlessly selecting values, plugging them in. If you're going to plot points, you got to plot the right points. And all of the interesting thing of this graph happens pretty much from about here to here, right? So I wouldn't need to plot very many points if I wanted accuracy. Okay? So far so good? Kind of cool. Now I want to go back to a problem we did last day so that we could fast forward a little bit. We did a problem last day involving a root. Help me out here. I think it was something like it's x to the, is it 2/3? 2/3 times x minus 5. Now, x to the 2/3, that's cube root of x squared. That does not have any restrictions. So everything was good. We were good with that one. Okay? I want to do this problem again because we want to do the same analysis we did because this problem is not going to be that uncommon, believe it or not. Or this type of problem, I should say. So I need to find the first derivative, but I don't want to differentiate the factored form. You factor things to set them equal to 0. For example, right now, everybody in here could tell me my x-intercepts are x equals 0 and x equals 5. That's easy. So 0, 0, and 5, 0 are very important points on my graph. But that doesn't help me for the derivatives. No, I want to distribute before I take a derivative. Otherwise, I got to use product rule with something ugly like this. That's more algebra than I want to do. So let's distribute. So I add exponents. So that's x to the 5/3 minus 5x to the 2/3. Now when I do my derivative, and by the way, we said this out loud, but let me write it. That is important because that is not always going to be the case. So my first derivative is 5/3 x to the, you can look at your notes, but I'd rather you do this from scratch. X to the 2/3 minus
10 over 3,
10 thirds x to the
negative 1/3.
-1/3. And before I try to set this equal to 0, I'm going to factor. So what is a common factor, or the best common factor? Well, probably 5/3 x to the,
Negative one.
gotta pick the smaller, so -1/3. Well, let's see, these differ by exactly 1, so that's just an x. Got all of that, and that would be a -2. At this point, by the way, it would be very wise for you to multiply this back out in your head. If I factored badly, then everything I say after this is going to be incorrect because I'm doing a different problem. It is always a good idea, check, let's see, add exponents, okay, boom, okay, good. If you're not checking, then you can make an error and you're never going to find it. Now, that's a negative exponent, so I'm going to rewrite this 5x minus 2 on top, 3x to the 1/3 on bottom. And that's important because the bottom, where it equals 0, actually is important, but it does not produce a horizontal tangent. The only horizontal tangent is going to come when x is 2. Okay? What's happening when x is 0? My derivative is, what's the word?
Defined.
Undefined. I'll put und. Now this is a tricky vocab thing. Undefined is when I'm taking non-zero and trying to divide it by 0. So as Noel was pointing out, I have a vertical line. That slope is undefined. If I'm outside the domain, we say that then the function is not defined. The square root function, because we're only dealing with real numbers here, the square root function is not defined less than 0, correct? Not defined means it's not in the domain. Not defined, undefined have absolutely nothing to do with each other and are rarely ever used in the same context. Undefined, I'm trying to divide by 0. Not defined just means I'm outside the domain. Now, my derivative is not defined at 0. Do you agree with that? 0 is not in the domain of my derivative, because my derivative would be undefined at 0. Oh my gosh. The square root function would be imaginary everywhere where it's not defined. It's not undefined anywhere. It would be imaginary if I put negative numbers in. I'm not defined at 0, but if I tried to evaluate the 0, my answer would be undefined. That's what I'm saying. That can be a little bit confusing at times. So we say the derivative is undefined at 0. Now here's why that's important. Because you said the domain was all real numbers. Here's a value where it's defined at 0, but the derivative is not. That's the evil kind of critical value. Those are the cool ones. Those are the ones that produce kind of interesting points, as we saw last day. Okay? This is how far we got last day. Now we want to do the first derivative test on this. And this one's going to be a little bit different. Now, the only time I'm ever 0 is here, but something weird happens here, so I consider both of them. The only place the derivative can change sign is at a critical value. It doesn't always change sign, right? It did there on the second one, but that's the only place it can change sign. So I can change sign in both of these places. Now, let's go that way forever. If I go that way forever, I'm going to have a negative on top and I'm going to have a negative on bottom. The cube root of a negative is in fact negative. Okay? So that quotient is positive. Now let's pick a number between 0 and 2, like how about 1? That's positive, but that's still negative. Now pick a huge number, bazillion, positive, positive. How many times do I change direction? 2 times. And I'm going to change direction at 0, which was the evil point. You say evil, I say cool. It was the cool point. Way cooler stuff happens there. And at 2. All right, so let's finish this part off. I had a green, here's my green. Okay. So we say f is increasing, f is decreasing. So where's f increasing? These two intervals, and they're always open. and it's decreasing here. I have seen textbooks give these as closed intervals. This is a problem. Okay, never write this down. But if I said it was increasing from negative infinity to 0 and I closed it, and then I said it was decreasing from 0 to 2, what am I saying? I'm saying the derivative is positive here, and it's negative here, and it's 0 here. You'd be saying the number 0 is both positive and negative at the same time. Is that a problem? Yeah, there's no number that's positive and negative at the same time. That you couldn't get a bigger contradiction. Or as I like to say at my house, you couldn't get any wronger. You can't be positive and negative at the same time, period. That's why this is incorrect. But I've seen textbooks do this, and that's not a good thing. No, they have to be open intervals. Now, this says I was going up. I didn't flatten out, but something interesting happened there, and then I turned around and came back down. So can I say that f of 0, which equals what, by the way? Equals 0 is a blank what? I went up, weirdness happened, and I turned around and came back.
X.
It's got to be a max. I went up, came back. It's got to be a max. I didn't get flat. I got pointy, actually. And then f of 2, which would be the cube root of 4 times negative 3. So I'll write that down. Negative 3 times the cube root of 4. I don't need a decimal. I'm not graphing. That's just the value. Is a blank what? Minimum. Now this might seem a little bit trickier to figure out absolute versus local. It's actually not. Go to here. X to the 2/3. Don't do this. Look at this. X to the 2/3. Is that ever negative? Cube root squared. That's never negative, is it? It's always positive unless I'm at 0. So as x gets big, as x gets huge, it's positive, positive, that's going up forever. Now what if x gets negative? That stayed positive, but now it's being multiplied by negative, it's going down forever. Does that make sense? So as x gets hugely positive, these are both positive. As x gets hugely negative, that's positive and that's negative, so it's going down forever. So that means that both of these they're both local because we just said we're going up forever and we're going down forever. It's the forever that's the kind of the key term there. So let's come back to this one now. Oops. Darn arrow. There we go. Now, I believe we drew this the other day. Is that correct? What's happening at the origin? What's that called?
Cusp.
That's called a cusp. I said it's pointy. It's sharp. It's not flat, but it did turn around there. How do I know it turned around there? Because it was a critical value? No, because I went from increasing to decreasing there. That's how I know it turned around there. And then the other one actually is a horizontal tangent. And because we can see that it goes up that way and it goes down this way, clearly they have to be local. But we didn't get that from the picture. The picture is confirming what we said. It's always got to be in this order. You've got to do all of your math, all of your analysis, tell me everything there is to know, then look at the picture. And hopefully, if you did everything right, the picture absolutely agrees. Now, you might have to change the window, right, to make sure that you see what you need to see. This window is okay, but you know, if it wasn't, I'd shrink the X or expand the Y or whatever I need to actually see what's going on. Clearly, this is the part that I need to see, because this goes down forever. In fact, it almost looks straight, doesn't it? Which is really odd. It almost looks linear at that point. It's not linear, but it kind of feels that way to a degree. Okay. Any question on this? So, first derivative test is to determine if it's a maximum or minimum by using the fact that I can identify increasing versus decreasing. All right? Let's keep going. We're killing this stuff. Now let's take something that's a little bit, I don't know, less friendly. In this context, I like using f of x rather than y for the simple reason that when you're doing f prime of a number, or later when we do f double prime of a number, the notation's easier than when you're using dy dx, vertical bar evaluated at. It's the same thing. That's just uglier notation. We all like f prime of 1. Yeah, that's just sometimes easier to write. So how about if we did something like, domain?
Is it anything but 0?
What happens if I take a log of a negative number? Take log of negative 1 for me on your calculator. Tell me what your calculator says. Is it an error?
Domain error.
Well, actually, you can take the log of negative 1, but it's not real. It's imaginary. Okay, now this is not a joke. We've said it before. We're only considering real valued calculus, which means we're only considering real inputs and real outputs. So when we're doing square roots, we're not putting in negatives. We can, but they'd be imaginary. Same thing with the logarithm. If we put in negatives, it would be imaginary. So therefore, what's the domain?
0 to
Positive numbers.
Only positive. Can I take the log of 0?
No.
You know, Chuck Norris was a former student of mine, and I taught him how to divide by 0 and multiply, you know, count to infinity and all that, but even Chuck can't do the log of 0. That's beyond everybody's skill. In any base, you cannot take the log of 0, so it's got to be strictly positive. That actually is important. You're going to get an error message on your calculator if you try to take the log of 0, but it's not the same type of error message because the log of a negative exists, it's just imaginary. Is that important? Actually, yes. We did a thing the other day, remember Euler's formula? Remember this? What's the sine of pi?
0.
0. What's the cosine of pi?
1.
The other way.
Oh, negative.
Negative 1. You know, you can win a bet at a party if you want. The log of negative 1 not only exists, but it's considered an extremely important result. The log of negative 1 is I times pi. If nothing else, it's kind of cool. Do we need to worry about that? No. Will we if you're engineers down the road? Oh, yes. But that's way down the road. Yeah, I can take the log of any negative number because I can always use this, but I'm going to get something imaginary. That's why we're not considering that for what we're doing. It's there, but not for graphing purposes. We're only graphing real things. So if a graph does not cross the x-axis, it means if there are x-intercepts, they would have to be complex numbers. That's what it means. And that's why we're not considering it. So in this case, if I only consider positive input, then I'm only going to get real numbers back. Okay, now let's do some derivative stuff, okay? Walk me through. Little product rule action here.
X times 1 over x times 1.
So plus, first time derivative, second plus, second times 1. I like that one. So that means this is 1 plus log x. I'd really like to know if and where this equals 0. Here, I did my part. Can you tell me where this equals 0? Actually, you can. Doesn't this mean that log x has to equal negative 1? So log base e of x equals negative 1 means x equals e to the negative 1. Or if you'd rather, 1 over e. Oh. So this has exactly one critical value. Remember, the log function is both positive and negative. It does change sign, so there's got to be a place where this adds up to 0, and it's going to happen when x is 1 over e. Now let's make our number line. So that's the only number on my number line, right? Left eye wink. That's the only number, right?
0.
0.
I kind of need the 0 because there's nothing to the left of 0. I've partitioned my number line into 2 intervals, but it's not negative infinity, it's 0 to 1 over e. 1 over e is only about 0.37, it's pretty small. And then 1 over e to infinity. This interval's really small, this one's really big. Huh, okay. Well, what does the logarithm graph look like? This will help you make your next conclusion. If I were to draw the graph, this is log any base, but if I'm doing this, I know it crosses at 1. It's a logarithm, so it looks like that, and then it looks like that. So the logarithm any base of a number between 0 and 1 is always going to be negative. But the closer I get to 0, can you answer this question for me? The limit as x approaches 0 from the right of the log x. Can you answer this? Negative infinity. That is very important. It doesn't approach a constant, it goes down forever. We're going to use that to our advantage when we can. So in this picture here, if I am really close to 0, then the logarithm is a really big negative number. So in here, big negative plus 1. Now as I go that way, log's getting bigger and bigger and bigger, and I'm adding it to 1. Does this graph change direction? Yes, it does. Add x equal 1 over e. Whoa. I mean, it's kind of crazy, but that's what it is. All right, let me get rid of this. I'm pretty much staying on this side so I don't have to put the screen up, at least not yet. Okay, so we can say that f is increasing, f is decreasing. So I'm increasing here. So from 1 over e to infinity, I'm decreasing from 0 to 1 over e, so not very long. Do I have an extremum? Am I going to have a maximum or a minimum? Yes or no? It's right there in front of you. Am I going to have a max or a min? What am I going to have? I have a minimum. And where's it going to occur? Here. I was going down, flattened out, went back up again. Oh, okay. So f of 1 over e, well, the natural log of 1 over e we know is negative 1. That's where it came from. Times 1 over e, so that would be negative 1 over e. Well, that's kind of boring. Is a blank what?
Minimum.
You said minimum. Now, there's nothing to the left of 0, and we know it's doing this. It only turned around once. Local or absolute? It's going to be absolute. It's turning around once. It's doing a. It's not a parabola, but it's more like that, and it's doing this kind of thing. I should say and absolute minimum. Okay. Now this brings an interesting question, one that we cannot answer exactly in this class. It's something you're going to learn how to answer next semester, but I'm going to give you a hint this semester. Okay? Some of you love to use L'Hopital's rule so far, which makes me laugh because you haven't used it in the right place yet. L'Hopital's rule exists for logarithmic and exponential limits because they can't be evaluated algebraically. And we're going to learn how to do this one next semester because we can't do it this semester. But the question is, what does this graph look like? So I'm going to make, this is going to be 1. I'll make one really big unit. Because I said 1 over e is about 0.37. My absolute minimum is going to occur right here, isn't it? Now, what's the natural log of 1? What's log any base of 1? 0. So when I evaluate this at 1, it's going to do this, because we said it's going to keep going up. The question is, what's going on in this direction? Well, you do know one thing. You know it turns around, right? Because we said it's decreasing. Does it go into the axis? Does it go into 0? Does it go up, maybe like vertical asymptote? We kind of put our hands up in there, don't we? But what's happening in between? Well, this will equal 0 when x is 1, agreed? Is there any other x value where this is 0? Well, remember I can't evaluate it at 0. 0 is not in the domain, so it's only going to cross the x-axis once. That means that graph has to stay below the x-axis. That means it's going into the y-axis, sorry. It's staying below the x-axis, so it's going into the y-axis, but it doesn't cross. So the question is, I'm gonna put a little dot, 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 where's it going? That means I need to know what is the limit as x approaches 0 from the right of x log x. You won't learn how to do this limit until about week 5 or 6 next semester. Okay, that's when you'll actually learn how to use L'Hopital's rule and what it's actually used for. It's used for that problem. There's actually only about 3 problems you're ever going to use it on in your life. And then you're never going to use it again, I hate to tell you, because it only works when there's one independent variable. And the restrictions on it are so astronomical that 99.997% of the time you can legally use it, it's the worst choice because it makes it infinitely long. You get in what are called infinite loops. You go forever without an answer. Yeah, algebraically is almost always easier and faster. I'd like to know what that is. We can't do this in this class, but we can kind of cheat. What do I mean by cheating? Do you remember when we first proved the limit of sine x over x as x goes to 0? I proved it geometrically. Then we looked at the picture. But then we had to do the e to the x minus 1 over x as x went to 0. And I showed you that we could see it. It had to be 1 because we said it's not asymptotic, it's not a break, it's not an endpoint, therefore it had to be removable. That was the only thing left. Well, this is either asymptotic or it's removable, but it's not going to be a break. It's not going to be an endpoint because I don't get to 0, so we're going to cheat a little bit. We can't answer the question algebraically, but this is one of those times we can use technology to help us. I don't know the answer, but I suspect that this is going to produce the answer for me. See, right about that, what did I say, roughly about 0.37? Look where we are. Are we about right there? 1 over e comma 1 over e. Everybody see it? Now, the graph is only defined for positive x values. I asked you, what do you think the limit as x goes to 0 from the right is? I don't know what the answer is, but as I zoom in and I zoom in and I zoom in, boy, it sure looks like that graph is heading towards what point? Does it look like it's heading towards the origin? Well, if it was asymptotic, would we see evidence? Would we see it going vertically? And we know it can't be asymptotic because we know it can't cross the axis. Therefore, removable is all that's left. Now, I said it had to go into the y-axis somewhere, but it's not going in at a random point. It sure looks like it's going in about here. So although we cannot answer this question yet, we suspect that this answer is what? 0. I can't prove that till next semester, but the answer is in fact 0. Will that help us get a more accurate graph as a result? Yes. Now, what if you said, God, it seems like, well, I mean, the log is approaching negative infinity. How can it be 0? I mean, I just don't see it. Well, the graph shows it. So there's something you can do. I believe the answer is 0 because I believe that I entered the technology correctly. Now, the technology isn't even like a proof, is it? But it kind of, remember, we said it's either asymptotic, it's not, we'd see it. It's going to be a break, we'd see a break. it's not an endpoint because I'm not actually defined, so removable is all that's left, and it sure looks like it's good. So what if I did this? What if I took the natural log of a really small number? I'll just take the natural log of, 1, 2, 3, 4, 5 zeros and a 1, and then I multiply that by 1, 2, 3, 4, 5 zeros and a 1. My calculator spit out a really small answer. If I entered an even smaller input, my calculator would return an even smaller answer, which is making me think, you know what? As my input gets smaller, my results are getting smaller. Boy, they sure feel like they're heading towards 0, don't they? Now, is that a proof mathematically? No, but if I wasn't sure, because really the only two answers anybody's going to get on this one, it's either going to be 0 or infinity, right? Because of what's happening. But it turns out it's 0, which is crazy. So how can it be 0? The log is going to negative infinity. Yes, it is. But the product is approaching 0. And again, we can't do it yet. It's something in the future. And by the way, I actually will do this problem specifically next semester. And a lot of you go, yeah, I remember. Now we finally get the answer to the question. It's kind of cool that we can answer things like this with minimum technology. We answered this question without the picture, by the way. The limit, I needed the picture because we don't have the math to do that limit yet. So we're kind of cheating using the picture to help us on the limit. Because you're not going to be asked that question this semester. Right? Let's do another one along these same lines. This will be the last one before we take a break. Partly because I don't want the recording to run out. It's got an upper limit. Now, I have a denominator, but my denominator is e to the x. Can e to the x ever equal 0? Or is it always positive? Therefore, do I have any restrictions in my domain? No, I have no restrictions. Is that important? Yeah, because that means my domain is what? Back to all real numbers. That's our favorite domain. I like that domain best. It means no restrictions, and I'm probably never going to get restrictions because e to the x is actually very friendly. Yes, it produces irrational numbers when I evaluate it, but in terms of derivatives, really nice. Now, I need to take the first derivative. So do I want to treat this as a quotient? No. How do I want to treat it? As a product. Remember, if your denominator is something raised to a power, writing it as a product will always be easier in this case. All right, so product rule. First, times derivative of the second. Well, the derivative of e to the thing is e to the thing times derivative of thing, which would be what's the derivative of thing? Negative 1. Yeah. The derivative of negative x would just be negative 1. Plus the second times the derivative of the first, which is
3x squared.
3x squared. I believe this factors very nicely. So x squared and e to the negative x, and what does that leave me with? Negative x plus 3. Could I leave it in this form? Yeah, sure, because the e to the negative x is never going to be 0, so I could leave it on the top. Or, if you don't like it on the top, I could rewrite this as, how about 3 minus x times x squared over e to the x. It isn't going to make any difference. Some of you might like it that way. It might just be easier to interpret. Okay? Will this ever equal 0? At 0 and 3. Everybody see that? Which is if we lose one of these, which is it probably going to be? It's always the same. Which one might not make it to the answer, do you think?
0.
The 0. For some reason, everybody sees the 3 minus x. That's not even a thing. But we see that, we don't sometimes. Our brain, I'm not joking, our brain doesn't process that. If this was a test question, everybody would get to there and half of us would lose the 0. We just wouldn't see it. I need to see x minus a number. Okay. So now let's make our number line. I only have two numbers, and it's the f prime. And it's important that you actually write f prime because next day we're also going to be doing second derivative, so there will be an f double prime number line in the same problem at the same time. We don't want to get confused. I only have two values, 0, 3. So I'm either positive or negative in every interval. So if I go left of 0, I go in a general that way direction. 3 minus a negative number is positive, positive, positive. Now take a number between 0 and 3. How about 2? 3 minus 2. It's still positive, isn't it? Positive. Ooh. Okay. Now take a number bigger than 3, like a bazillion.
Negative.
Oh. Do I change direction? How many times? Once. Where am I going to change direction?
3.
At x equal 3. Everybody got that? It's sitting right there, jumping off the page, screaming at you. Well, figured. So I can say that f is increasing and f is decreasing where? I'm increasing negative infinity to 0, and then again from 0 to 3. I'm not increasing at 0. I have a horizontal tangent at 0, which we'll see in a moment when we bring up the picture. And I'm decreasing 3 to infinity. You said I changed direction once, and it's right here. So f of 3, which equals what? F of 3 is 27 over e cubed. That's not a very big number, by the way. I mean, e cubed, I think, is around 20, so that's a very small fraction. This says I went up, I was flat, and I came back down. So is this a maximum or a minimum?
Maximum.
So I'm not going to commit.
It's a maximum.
It's a maximum, yes. If you're having trouble with that, at the peak of a mountain, I'm a maximum. Well, as x gets bigger and bigger and bigger, x cubed is going to get bigger and bigger and bigger, but e to the x, I think, is bigger. How do I know that e to the x is bigger? Because the bigger x gets
Smaller.
Doesn't this say this is going downhill? Ooh. What if x is negative? This is tricky. If x is negative, then I have e to the negative, which is really small. When I bring it up, it means it's huge. But that's also negative. So is it going down forever, or is it going up forever? It's going down forever, because when x is negative, this quantity will be huge. If you put it at negative 10, this will be astronomically large, but negatively. Oh, so this says I'm increasing, something happened at 0, I continue to increase, and then I'm going back down. This is not a very big number, but it is absolute. Does that kind of seem odd? But now look at the behavior. I went up, flattened, up, came down. It has to be the highest point. Again, it's confounding at first because our common sense, but remember, e to the x, an exponential function is going to grow much, much, much faster than the x cubed. Okay? So I'm not expecting but something else happens in this one that's actually very, very cool. We don't know how to answer this question yet. Again, this is a next semester thing. But as x gets big, I'd like to know what is the limit as x approaches infinity. This is clearly the indeterminate form infinity over infinity, but I can't use degree on the bottom because it's an exponential function. But if you believe that the exponential function is growing so much faster than the x, if you're not sure about that the exponential is growing much faster, I'm going to put a small number in. I'm going to put in 10. 10 cubed over e to the 10th is approximately 0.04. Now I'm going to put in 100. 100 cubed over e to the 100th. My calculator says it's on the order of 10 to the negative 38th power. So by the time I'm 100 units out, I'm 37 zeros after the decimal place for my y value. Those numbers are getting really small, and they're positive. What do you think that limit is?
0.
0. And again, I'm cheating because I'm using technology to give me an idea, because we can't answer this question till next semester, so don't be telling us a real problem. Which nobody in this class actually knows how to do in this case. But let's graph it now. You're going to like this, because the stuff that we can answer now, and how many ever actually use Desmos or any computer things to look at? If you have a graphing calculator, that's good enough, right? Because you can be anywhere and do that one, but you got to be at a computer to make this work, and I wouldn't do this on a cell phone. Way too small. Okay, x cubed. Okay, so now I need to x cubed over e to the x. Oh, shoot. All right, I need to change the y scale just a little bit. Oops, here we go. Where did we say our maximum was? Yeah, 3. Oh, no, I don't need to change the y scale. Here we go. I just need to go this way a little more. Here we go. Now, I just said a moment ago, when x gets big negatively, this is going to get huge, but negatively. That means it's going down forever. I'm not going to, I can look at this, this is going to go like this. We know that it's not that interesting. I want you to look at what's happening to the right. That was our peak. Look how small that is. That's like 1.4 or something, 1.3. It's not very big, but it's the highest we got. And then what's happening? It's starting to tail off. Can you see it? The x-axis is a horizontal asymptote. The graph of y equal e to the x, isn't the x-axis a horizontal asymptote? Yeah, that's why, so as x gets bigger and bigger and bigger, this quotient is getting smaller and smaller and smaller. It's never equal to 0. It's always positive, but it's getting so small. I went out 100 units and we said it was 10 to the negative 38. That's pretty small. So to the naked eye, it looks like it's just gone right into the x-axis, doesn't it? Okay, that's not a proof. No, that's a demonstration of the fact that that is in fact the limit. I know what the limit is because I have the higher class. I know what the limit is. I'm just sort of easing you guys along. But isn't that cool that we know that exactly? Okay? Any question on this? So our ability now is, given any function that we can differentiate, which is could be pretty much anything, we can determine where the extrema are by using the first derivative test. That means that I had to be able to factor the first derivative. So if you had something so complicated that it couldn't be factored, we're going to stay away from that type of problem, because you're not going to get anything out of that one. Okay? All right, let's go ahead and stop that and do the roll thing.